Now let us see this one more phenomenon of light. It also uses the wavemeter. Light travels in the form of transverse electromagnetic waves. Light travels along the straight line path. So using wavemeter, we are going to explain this one more phenomena called as the diffraction of light. Now what is meant by diffraction, that we have to explain. So we will consider a simple experiment. There are two parts of the experiment like this. Suppose this is the source S and this is the screen of observation. Now, if we consider a one more screen having the slit, so this portion is open. So light rays from S will pass in the direction like this. The uppermost ray passing through the point A, it will touch the screen at point A1. This is the slit AB. So the uppermost ray is passing to the point A and it will touch the screen at point A1. The lowermost ray will pass through the point B and it will touch the screen at point B1. So this is the experiment A. So in this case, the waves from the source are reaching all the points between A1 and B1. So this A1, B1 is the illuminated area. Illuminated area of the screen. Now, above the point A1, there are no waves reaching, so this is the region of geometrical shadow. Geometrical shadow. Same thing is here. No light waves can touch the screen below B1, so this is again the region of geometrical shadow. Geometrical shadow. This is the screen of observation. Screen of observation. This light wave has wavelength lambda, and this distance between A and B, it is D. So D is a width of the slit AB. Lambda is a wavelength of the light used here. It is a monochromatic light. A1, B1 is the illuminated area. Illuminated area of the screen, and above A1, below B1, there is a condition on either side of A1, B1. there is geometrical shadow. There is a geometrical shadow, means darkness. So these are the observations, but there is a condition. When the width of the slit is very much greater than lambda. Now, second part, when d is comparable with lambda, then what will happen? So these observations are different. So this is the A experiment. The monochromatic light from the source is passing through the slit AB whose width is d. So light waves are passing through this. So in this portion, the light waves are reaching all the points between A1 and B1. So this is the illuminated area of the screen. Above A1 there are no light because light propagates along the straight line path. Light propagates along the straight line path. So below SB1 no light waves. Below SA1 there are no light waves because this is a non-transparent part of the slit, and therefore we get the illumination between point A1 and B1 in the region A1 B1. Above A1 there is no light wave, geometrical shadow. Below B1 there is no light wave, there is a geometrical shadow when d is very much greater than lambda. Now if d and lambda are comparable, then there is a change in observation. What is the change in observation? That we will see afterwards. Now experiment B. Here again we are using the screen of observation. This is the source S. Now this is a non-transparent object. Its height is same. So the rays of light from S passes through the A and it strikes the point A1. The another lower force ray is passing to the point B and it strikes the screen at point B1. So this is a non-transparent, opaque, non-transparent object. It may be an object like pen. It may be an object like a duster, like this. So in this case, between A1 and B1, there is a geometrical shadow. In this portion, there is a geometrical shadow. Geometrical shadow. Above A1, there is a illumination. Illuminated area. This is the illuminated area. Illuminated area and geometrical shadow का area interchange हो जाएगी. Illuminated area. This is the screen for observation. This AB has the width D. This has wavelength lambda, like this. So again, D is the height of the non-transparent object, lambda is the wavelength. So इथे फक्त change झाला. D is equal to height of an opaque object. So in this case, the positions of the geometrical and illuminated area are exactly reversed. In this case, above A1, below B1, there is a geometrical shadow. In this case, above A1 and below B1, there is a illuminated area, because the light waves from the source can reach directly all the point below B1, all the point above A1. But this is a non-transparent object, so rays of light cannot pass through it. Therefore, there is no light waves reaching in the region A1, B1, and therefore there is a geometrical shadow. So, only the change is here. D is a non-transparent object, height of the non-transparent object, and AP is a width of the slit. So, light waves can pass, light waves cannot pass, and therefore the position of the geometrical shadow and illuminated area get interchanged in both the cases. Now, in this case, first, when D is very much greater than lambda, then on either side of top and bottom side, lower and upper side, on either side of A1, B1, there is a illuminated area. And A1, B1 is the geometrical shadow. Of the object AB. Like this. Now, in this case again, if we decrease the height of the object, if we decrease the width of the slit, what will happen? So, this second case is important. When D is comparable with lambda, then if D is comparable with lambda, then what will happen? So, in the first case, some light waves enter into the region of geometrical shadow upon A1. So, they bend at the corner and they enter into the, when D is comparable with lambda, then the light waves passing through corners A and B bend and कुठल्या साईडला बेंड होत आहे and enters the region of geometrical shadow, means above A1 and below B1. The light waves passing through the corners A and B bend and enter the region of geometrical shadow. Now on this side, in this case when D is comparable with lambda, then the light waves passing through the corner A, they bend in the downward direction, they also enter. So same observation, when D is comparable with lambda, then light waves passing through corners A and B bends and enters into the region A1 B1 of geometrical shadow. So some waves bend like this. Some waves bend like this. In this case, the waves bend above. So this phenomena of bending of light when passing through the corners or edges is called as diffraction. So this bending of light is called as the diffraction. The single word मध्ये आपल्याला diffractionचा meaning माहिती आहे. Diffraction means bending of light, or it is a non-rectilinear propagation. There is no change in medium before passing to the point A, after passing to the point A. Before passing to the point B, after passing to the point B, there is no change in medium. There is a medium air. Here is the air medium, there is the air medium, air. So without any change in medium, the rays of light bend. आपल्याला बेंडिंग ची फेनॉमेना माहिती आहे, रिफ्रॅक्शन ऑफ लाईट, पण तिथे मीडियम चेंज होतो. ड्यू टू द चेंज इन रिफ्रॅक्टिव्ह इंडेक्स देयर इज अ बेंडिंग ऑफ लाईट. दॅट फेनॉमेना इज कॉल्ड द रिफ्रॅक्शन. हियर देयर इज नो चेंज इन मीडियम, देयर इज नो चेंज इन रिफ्रॅक्टिव्ह इंडेक्स, स्टिल देयर इज अ चेंज in the direction bending of light. This phenomena is called the diffraction. So refraction and diffraction, these are the two phenomena of light in which there is a bending of light, but the reasons are different. The height महत्वाचा पॉइंट आपल्याला माहिती पाहिजे. So this phenomena of bending of light at the sharp corners is known as diffraction of light. So diffraction is non-linear, non-rectilinear propagation. The phenomenon of bending of light at the sharp corners of the slit or the edges of the object and spreading of light. Light bend होतो, कुठे जातो तो geometrical shadow जातो. The spreading of light into a region of geometrical shadow. Region of geometrical shadow is called diffraction of light. Diffraction of light. So actually this is the definition. Definition of diffraction of light. So these are called as the diffracted rays. In this figure, these are diffracted rays. Diffracted rays. In this case, these are the diffracted rays. Diffracted rays. But this condition is important. When D is comparable with lambda, then and then diffraction takes place, otherwise there is no diffraction. So these are the observations to explain the phenomena of diffraction of light. So remember the observation. In case A, in experiment A, so we know that light are electromagnetic waves and they travel along the straight line path. But they travel along the straight line path when, in this case, width of the slit, and in this case, height of the object is greater than wavelength of the monochromatic light used. So wavelength is of the order of 10⁻⁷ meter, and this D is sufficiently large in this case. Now, if we decrease the width of the slit, if we decrease the height of the object, non-transparent object, then when D becomes comparable to lambda, the observations are completely different. Some light waves passing through the corner A and B, they bend. So now they are not traveling along the straight line path. They bend means they are not traveling along the straight line path. So this bending of light, this phenomena is called as a diffraction. These are the diffracted rays. These are the blue color. These are the diffracted rays. So this is called as the diffraction. So in single word, you can give the meaning. Diffraction means bending of light. Diffraction means non-rectilinear propagation of light. So you can add here. So diffraction means bending of light. Or it is the non-rectilinear propagation of light. Non-rectilinear propagation of light is called as the diffraction. So refraction and diffraction, these are two phenomena where bending of light is observed, but the results are different. Now, what is the change in these two phenomena that we want to explain? So, now we want to compare these two phenomena, refraction and diffraction. Bending of light takes place. Bending of light takes place due to change in medium or due to change in RI, refractive index of the medium on this side. Bending of light takes place without any change in medium, but D should be comparable with lambda. So this is the condition. Change in medium, this is the condition. D must be comparable with lambda, this is the condition. So this is the necessary condition for the diffraction. So now this condition is important. This diffraction and bending of light or non-rectilinear propagation, through this corner the light will bend like this. They do not move along the straight line path like this. Now, what is the necessary condition for diffraction? Necessary condition for diffraction. The condition we already know. Diffraction is observed. Diffraction of light is observed only when size of the object or size of the width or height of the object is comparable with wavelength lambda of light. Of course, it is a monochromatic light. that is mathematically d is comparable with lambda. This is a necessary condition. D is comparable with lambda. So d is a size of the diffracting element like slit, non-transparent object, like this. So in general, the object which diffracts the light is called as a diffracting element or diffracting object, and it has this condition: either this transparent part of the object, that is called as the width of the slit, or height of the non-transparent object, they should be comparable with the wavelength lambda as shown in the figure, like this. So this is necessary condition. Necessary condition for this diffraction. For now, here we can compare the two diffraction phenomena. For sound waves, objects of size d comparable with lambda, comparable with wavelength of sound, are possible because lambda for sound waves is larger than light waves. Therefore, diffraction of sound waves take place easily than light waves. That is, diffraction of sound waves is predominant than light waves. So both the waves are diffracted. So there are so many phenomena that are commonly exhibited by light waves as well as sound waves. Interference is also one example. Interference, diffraction, reflection, refraction. Only polarization is the distinguishing phenomena. Sound waves cannot be polarized, light waves can be polarized. So this is a specialty of the polarization phenomena, like this. So this is about the basic concept of diffraction. Diffraction means change in the direction of the light waves when they passes through the corner of the sharp corners of the slit or edges of the non-transparent object, like this. So in the very first part of this chapter, we have seen the nature of the light. Light has dual nature, particle nature as well as wave nature. So using wave nature, we are explaining some phenomena, and those phenomena are like this. Wave nature of light is used to explain following phenomenon. Following phenomena of light. 1. reflection, second, refraction, third, dispersion, fourth, polarization, fifth, interference, sixth, diffraction. So these are the phenomena that we can explain using the wave nature of light. So each phenomena has certain characteristics, and depending upon that characteristics, so in a single word you can do the meaning like this. A reflection means bouncing back of light into same medium. A refraction means bending of light, due to change in medium. Dispersion means splitting of light. Polarization means a restriction. The interference means superposition. Interference means distribution of intensity. Non-uniform distribution. Of light energy. And diffraction means bending of light. This bending of light or non-rectilinear propagation of light, like this. So these are the phenomena that we can explain using the wave nature of light, and their meaning in single sentence are like this. Refraction means bouncing back of light into the same medium, like this. Now, in case of interference, we have seen two types: constructive interference and destructive interference. In this case, the phenomenon of diffraction of light was observed by so many scientists, and there are various methods to observe the phenomenon of diffraction of light. So, depending upon the observation, the diffraction phenomena can be studied in two ways. One given by or explained by the scientist Fraunhofer, and other one is the Fresnel. We have seen Fresnel's biprism experiment. The same scientist has also observed the phenomena of diffraction of light, and he has explained this phenomena of diffraction like this. So there are two types, one suggested by Fresnel and other by Fraunhofer. So the two types are like this. Fraunhofer's diffraction and the second one is Fresnel's diffraction. Fresnel's diffraction. So what are the distinguishing points between them that we are going to see? First point. The wavefront used to observe diffraction is a plane wavefront. On this set, the wavefront used to observe the diffraction is spherical or cylindrical wavefront. The main difference is this. Here we are using plane wavefront, here we are using cylindrical or spherical wavefront. So we know the methods. Plane wavefront is obtained by keeping the source of light at infinity, and spherical or cylindrical wavefront are produced by using a source of light at finite distance. So when we are to observe this diffraction phenomenon, what is the arrangement? We require source, we require screen, and here this is a diffracting element. This diffracting element, we know it may be a slit, it may be a non-transparent object. So this distance is x, this distance is y. So when we are to use the plane wavefront, then what is the condition? Either the source should be at infinity, means x should be infinity, or y should be infinity. So when x is infinity, very very large, y is infinity, very very large, then we get the plane wavefront, and the type of the diffraction is the Fraunhofer diffraction pattern. So when the distance of the primary source and the screen used for the observation from the diffracting devices like slit are effectively very large, then it is called as a Fraunhofer diffraction. So according to this figure, what is the condition? When the source S, of course primary source, because there are secondary sources, when the primary source is at very long distance from diffracting element, or when the screen of observation is at very long distance, infinite distance from diffracting element, like slit, then the type of the diffraction is called, Fraunhofer diffraction. So plane wavefront is produced by this method. Now on this set, we are using spherical. So the source or the screen both are at finite distance. The source and the screen, when the source or the screen of observation are at finite distance from diffracting element, then it is Fresnel's diffraction. Finite distance means the wavefront is spherical or cylindrical, like this. Now the third point. To observe this Fraunhofer diffraction, observations are made by using lenses or mirrors. Lenses or mirrors are used to observe Fraunhofer diffraction. Diffraction. On this side, there is no use of lens or mirror. Third, no lenses or mirrors. No lenses or mirrors are used to observe Fresnel diffraction. So these are the two methods to observe the phenomenon of diffraction, like one suggested by Fraunhofer and other suggested by Fresnel. So out of these two, only Fraunhofer diffraction is included in our syllabus. So we have to study this Fraunhofer diffraction in detail. This is not included in your syllabus. So these are the conditions. We are using plane wavefront. So while explaining this Fraunhofer diffraction, either using single slit, double slit, etc., we are using plane wavefront. And to produce the plane wavefront, these are the conditions. And here lenses or mirrors are used like this. So we are going to see this Fraunhofer diffraction in detail. Fraunhofer diffraction can be produced by using either single slit, double slit, or very large number of slits, infinite number of slits, like this. So to observe this phenomena of diffraction, the simple arrangement is like this. There is a source, there is a diffracting element, and there is a screen of observation, like this. So this Fraunhofer diffraction is observed by using simple experimental setup. S is a monochromatic source of light. O is a diffracting element. Like slit, non-transparent object, double slit, etc. AB is a screen for observation. Screen for observing diffraction pattern. Diffraction pattern, like this. So in any type of diffraction experiment, these are the basic elements: source, diffracting element, and the screen used for the observation of interference pattern like this. So next time we will see the Fraunhofer diffraction using single slit like this.